little book of cosmology. I got this from the library as well, and I do have to return it at some point soon. Now, I think that a lot of the topics in this book are basically review, and we've covered it already. But just to make sure, I thought that we will cover a little bit about the Friedmann equations from this book and comment on the parts that we've already seen or whatever we think. And let me know your comments in the chat as we keep going. And if you want to talk about something else, go for it and make friends in the chat and whatnot. Okay? The Friedmann equation can be thought of as expressing the law of conservation of energy for the universe as a whole. So that's what this guy, Peter Cole, is saying. Actually, his name is Peter Coles, C-O-L-E-S, and he's got this very little book on cosmology that we will now read from. Cosmology is the study of the universe, as opposed to cosmetology, which is the study of makeup and hair and things like that. So cosmology is the study of the cosmos or the universe, something like expansion of the universe due to dark energy, large-scale structure, cosmic microwave background radiation, Big Bang, those types of things fall under cosmology, okay? So that's what we're going to read about right now. We'll get going. We'll keep going. So the Friedmann equation can be thought of as expressing the law of conservation of energy for the universe as a whole. Energy comes in many different forms throughout nature, but only two relatively familiar forms are involved here. A moving object, such as a bullet, carries a type of energy called kinetic energy, which depends upon its mass and velocity. So if you are sort of familiar with kinetic energy, if you took a physics class or something like that, you would know that kinetic energy, of course, depends on mass and on velocity. Something like 1/2 mv squared, if you remember an equation like that. Obviously, since the universe is expanding and all the galaxies are rushing apart, the universe contains a great deal of kinetic energy. So we know that there's expansion in the universe. We've talked about it, and how things that are far, far away are actually getting farther away because of the expansion of the universe. And so there is quite a bit of kinetic energy. The other form of energy is potential energy, which is a little more difficult to understand. Whenever an object is moving and interacting through some kind of force, it can gain or lose potential energy. So maybe you've heard of something like gravitational potential energy, or potential well, or the gravitational potential energy of a black hole or a star, or even our sun basically has a gravitational potential energy. For example, you might have heard of such a thing. So that's the other type that this author is pointing out. This is sort of the take on this topic by this author. So sometimes we read about the same thing from various authors so that we can kind of get various different perspectives, which hopefully will help with our understanding. But a lot of this is kind of like review as well, okay? For example, imagine a weight tied on the end of a dangling piece of string. This makes a simple pendulum. So everybody's seen a pendulum. If I raise the weight, it gains potential energy because I have to work against gravity to lift it. So if you raise the weight of a pendulum, of course, and then you release it, then it will begin to swing. If I then release the weight, the pendulum begins to swing. The weight then picks up kinetic energy, and as it drops, it loses potential energy. So as it's at the top, it has a lot of potential energy against gravitation, and as you drop it and it starts to move, it basically gains kinetic energy, and that potential energy is kind of converted to kinetic energy. Energy is transferred between the two types in this process, but the total energy of the system is conserved. The weight will swing to the bottom of its arc where it has no potential energy, but it will still be moving. Okay? It will in fact describe a complete cycle, returning eventually to the top of its arc, at which point it stops instantaneously before starting another swing. So it's kind of like a constant transfer of potential energy to kinetic energy to potential energy that happens in a system like this, simple pendulum. At the top, it has no kinetic energy. So for a moment when it's at the top, it's actually stopping, right? So stopping means the velocity is 0, so 1/2 mv squared is 0 because v is 0. So it has no kinetic energy at that point, and all of the energy is now potential energy at the top of the pendulum. And then as it starts to move, some of that potential energy is converted to kinetic energy, right? So this is all sort of explaining what's happening with the energy of this simple system and how it kind of transfers between kinetic and potential energy. Wherever the weight is, the energy of this system is constant. So this is a simple example in a simple pendulum system where the energy is conserved, and we kind of get it very easily because we can kind of see, we can picture it in our minds, or you can even interact with a simple pendulum to understand what we're saying, okay? This is the law of conservation of energy, okay? So, in cosmological terms, the kinetic energy depends crucially on the expansion rate, or in other words, upon the constant h naught. This is called the Hubble constant. So now remember, Hubble is the astronomer who told us about other galaxies, who actually with his observations of this universe gave us the expansion of the universe, as well as the discovery of many other galaxies and other basically these other worlds. World generally means a planet in strictly speaking in astronomy, but this whole sort of knowledge that our galaxy is one of many, and in fact if you peer in the universe, you see many other galaxies, was something that's quite new to us back about 100 years ago. We did not know that there were so many galaxies out there, okay? So that's who Hubble is. Thank you so much, by the way, for being here. Welcome to the live, and please do like the live. Please do double tap for liking the live. But this guy Hubble, of course, a very important guy in astronomy, and we have named this expansion rate called expansion rate after him, Hubble constant. The potential energy depends on the density of the universe, that is, upon how much matter there is per unit volume of the universe. So energy density of the universe is something that comes up a lot in what? Energy density is something that comes up a lot. Hello, Ekjin22. Okay, energy density is something that comes up a lot in terms of cosmology. It is something that is often used to understand and measure different cosmic ingredients and measure sort of the makeup of the universe. By the way, we have entire episodes on cosmology where we talk about the cosmic ingredients and the cosmic makeup of the universe. So when we talk about the cosmic makeup or the cosmic inventory or the cosmic what makes up the universe, it's actually 5 main ingredients, and we've talked about this real quick. These are photons, baryons, neutrinos, dark matter, and dark energy. So just 5 types of things are there in the universe. Photons, as you know, it's light. Neutrinos is a very weakly interacting lepton particle that was discovered at some point and used to be considered a candidate for dark matter, but turns out that dark matter is probably not accounted for by neutrinos, but it is a sort of weakly interacting introverted particle that's in the same family as electrons. Baryons are ordinary matter. Most of the matter that you and me, you and I, everybody, everything is made of. Most of the matter that we know and understand is baryons. These are neutrons and protons. Dark matter is the invisible matter that we find in this universe, in this galaxy. It's the extra matter that seems to be there, but we cannot see it. It does not interact with light, but it does interact with gravitation, so we call it dark matter. And turns out that most of the matter is dark matter in the universe, and then dark energy is what allows or what makes or what is responsible for the expansion of the universe. Because remember that the universe has, of course, gravitation. There's this universally felt force or phenomena of gravitation, which should be making things come closer. But in fact, the universe turns out to be expanding. Ooh, there's Baji. So what makes it expand? This is a topic of interest. It's a topic of research, and it turns out to be dark energy, and that's our 5th cosmic ingredient. Now, when we talk about energy density, these ingredients will come up, and that's why I give you a little spiel on them right here, right now. So once again, the cosmic ingredients are photons, baryons, neutrinos, dark matter, and dark energy. You know what I'm going on about because this is cosmology and we've covered it before. Come on now. J with an E. Good. Exactly. J with an E, you should probably do your homework and stop being rude to women on the internet. And mom loves you and dad loves you. Okay? I don't want to time people out because I really need the watch hours. I'm keeping my word by posting my book on Instagram one chapter at a time. So Stephen, I was telling Stephen Doro that his book is actually stories right now instead of posts, and I think by mistake he posted the book as stories rather than posts, okay? What? So the sun cooks the ingredients. So the sun actually cooks hydrogen to make helium. So the sun burns hydrogen. It does nuclear fusion of hydrogen to make helium. That's what the sun does. So what the sun does is sort of a subset of what all of this is. The sun is astronomy. So remember, we're talking about cosmology now, which is sort of a much more large scale topic. It's the topic of the universe. So there's the universe, and what are the 5 ingredients of the universe, which is really a very basic and very like foundational way of talking about the universe. It misses a lot of the details, right? So when you talk about the sun is really a detail in the universe. It's a very detailed little specific thing when it comes to the entire universe, right? We're talking about the universe as in when galaxies weren't, like the evolution of the universe comes, starts from the Big Bang to now, and at one point there were no galaxies, there were no stars, there was no sun, things like that. So I would say that what the sun does is kind of falls under astronomy and nuclear physics and nuclear astrophysics and astrophysics. So yes, it burns hydrogen and it utilizes hydrogen to make helium, and that's basically the nuclear power plant in the belly of the sun, which makes the sun burn and the sun glow and the sun give us light and energy and heat and all that. But it doesn't necessarily involve all of the ingredients of the universe. Although I will say, good point, it does involve neutrinos. So neutrinos is it's a particle that is generally emitted in every nuclear reaction. So it's very commonly made in a lot of nuclear physics types of interactions. Like pretty much no matter what you do, you end up making a neutrino. So actually, the sun involves 3 of the 5 ingredients. So you're not far off. The sun involves photons, obviously light, baryons, of course, because it involves neutrons and protons, and it does involve neutrinos. So those are 3 of the 5 ingredients of the universe. So in that sense, not far off. But the universe as a whole, turns out, involves a lot of dark matter, which we didn't think it would, but it does. And it also involves dark energy, and it involves dark matter and dark energy mostly. Turns out ordinary matter is only like 5%, and everything else is dark matter or dark energy. Okay, so with that little spiel about the cosmic ingredients, we'll go back to understanding what the energy density of the universe is. So this is going to be a little bit different than what you might be thinking, so just kind of stay tuned here. So in cosmological terms, the kinetic energies, we just looked at the simple pendulum example of where the energy was being conserved between potential energy and kinetic energy. At the top of the pendulum, the energy is all potential energy and the kinetic energy is 0, but as it starts to move, some of that potential energy is converted to kinetic energy, and the total energy of that system in that simple pendulum system is always conserved. In other words, the same sort of thing is expected in the universe. So let's see what he has to talk about in terms of energy density here. So the potential energy depends on the density of the universe, that is upon how much matter there is per unit volume of the universe. Unfortunately, this quantity is not known at all accurately. It is even less certain than the value of the Hubble constant. If we knew the mean density of the matter and the value of h naught, which is the Hubble constant, however, we could calculate the total energy of the universe. This would have to be constant in time in accordance with the law of conservation of energy or in this context, the Friedmann equation. Fusion, not fission. What do you mean? Heike and Noindri has seen it. Yes. Yes, your book is in your stories. Where were you with that beautiful dress? Which one? Fusion. So you're correct that the sun is doing fusion. Fission is what the atomic bomb is. Human beings figured that one out, but the sun mainly does fusion. Correct. If that's what you're asking about. Okay. So if we knew the mean density of matter and the value of h naught, however, we could calculate the total energy of the universe. This would have to be constant in time in accordance with the law of conservation of energy, or in this context, the Friedmann equation. Setting aside the technical difficulties that arise when general relativity is involved, we can now discuss the evolution of the universe in broad terms using familiar examples from high school physics. So he's kind of relying on some analogies here, I think, going forward in sort of explaining what goes on with this universe math. But it's not going to be exact because the universe, of course, involves general relativity, which has some complicated equations. So he's kind of bypassing that and giving you sort of an analogous type of example, okay, to explain things. Thank you so much for being here in the live. Can you please double tap and like the live? For instance, consider the problem of launching a vehicle from Earth into space. Here, the mass responsible for the gravitational potential energy of the vehicle is the Earth. The kinetic energy of the vehicle is determined by the power of the rocket we use. Because, of course, when a rocket is being launched from the Earth, the gravitation that it has to surpass is the gravitation of the Earth. And the Earth has a gravitational potential energy that it has to kind of escape, right? And we give the rocket fuel so that it can have kinetic energy. So whenever something moves, it has kinetic energy. And if it is kind of overcoming the gravitational potential energy to have that kinetic energy, that's what this is kind of talking about. So if we give the vehicle only a modest rocket so that it doesn't move very quickly at launch, then the kinetic energy is small and maybe insufficient for the rocket to escape from the attraction of the Earth. Consequently, the vehicle goes up some way and then comes back down again. In terms of energy, what happens is that the rocket uses up its kinetic energy, given expensively at launch, to pay the price in terms of potential energy for its increased height. If we use a bigger rocket, it would go higher before crashing down to the ground. Eventually, we will find a rocket big enough to supply the vehicle with enough energy for it to buy its way completely out of the gravitational field of the Earth. So by the way, guys, does anybody know the escape velocity from the Earth? So if you go a certain high velocity, then you can actually escape and kind of get into orbit around the Earth. But you would have to have enough kinetic energy to kind of not be trapped back and fall to the floor or fall to the ground again on Earth, okay? Eventually, we will find a rocket big enough to supply the vehicle with enough energy for it to buy its way completely out of the gravitational field of the Earth. So this is the analogy that we're going to be using. The critical launch velocity here is usually called escape velocity. Above the escape velocity, the rocket keeps on going forever. Below it, the rocket comes crashing down again. So this is what I was just talking about, and he kind of said it himself, which is that, of course, if you want to escape the Earth, you would have to be going at an escape velocity. And if you want to come crashing down, then you can go at below that escape velocity and you will fall back down to the Earth. But if you go above that, then you will actually escape. In the cosmological setting, the picture is similar, but the critical quantity is not the velocity of the rocket, which is analogous to the Hubble constant and is therefore known at least in principle, but the mass of the Earth, or in the cosmological case, the density of matter. So this rocket business that we just talked about, the rocket, the Earth, the gravitational potential energy of the Earth, and the kinetic energy of the rocket, all of this is sort of an analogy of what we're about to talk about with the universe and whatnot. This is just Peter Coles' way of explaining to you what some of this is with the universe. So just hang in there, hold tight. So in the cosmological setting, the picture is similar, but the critical quantity is not the velocity of the rocket, which is analogous to the Hubble constant and is therefore known, at least in principle, but the mass of the Earth, or in the cosmological case, the density of matter. So the density of matter is going to be important. It is therefore most useful to think about a critical density of matter rather than a critical velocity. If the real density of matter exceeds the critical density, then the universe will eventually recollapse. So this is sort of getting to that point of expansion versus recollapse versus not expansion too fast versus expansion too fast, things like that. We've kind of actually looked at an example of this. Remember those curves I showed you a while ago? They're in my shorts as well, and somebody's been recommending that I turn the camera or something because things have come up inverted because of the camera being whatever. But I'm about to show this to you again, probably inverted again, but I think you'll get the idea, which is that basically if the real density of matter exceeds the critical density, then the universe will eventually recollapse. So if the expansion of the universe is slow, then it will recollapse. If it's very fast, it will never recollapse. And if it is sort of a critical rate, then it will do some currently known type of expansion. So we will see, right? So again, if the real density of matter exceeds the critical density, then the universe will eventually recollapse. Its gravitational energy is sufficient to slow down, stop, and then reverse the expansion. So recollapse would mean that there has been expansion, but it would slow down, stop, and then reverse the expansion, meaning it would collapse upon itself. And this is exactly, by the way, what people asked about when Einstein was doing his general relativity equations for the universe, and he was asked to consider, well, if the universe has gravitation, and gravitation is always an attractive force, it's always attractive, it's universal, everything feels it, and it's always attractive, it's never repulsive. So why is the universe sort of steady? Why doesn't it collapse upon itself? And so he had to introduce the cosmological constant to kind of give his equations this constant to keep the universe static against gravity, an anti-gravity term. But turns out that not only is the universe not static, it's actually expanding, which begs the question, what kind of expansion rate do we have? Because if something is expanding slow enough, then it could be that, sort of like that rocket, it could be that it expands, the expansion slows down, then stops, and then reverses, which would be a recollapse. Yes, of course. Yes, they're generally exoatmospheric. ICBMs, of course, ICBMs are generally exoatmosphere. They absolutely go out of the atmosphere first. I'm not talking about ICBMs right now in the Steven, did you become a member? Oh my gosh, thank you so much. I think you're my first member. Welcome. I'll make content just for you. I'll have to make member specific content. I'm getting there, but thank you so much for becoming a member. Wow. Just letting you know, I have put my little white friends in storage. What? What do you mean? I thought it was Harper banning everyone. So Grimmy, I'm talking about cosmology, but this guy whose book we're reading, called Peter Coles, who has written a very tiny book on cosmology that I got from the library, he is using the analogy of rockets and potential energy and kinetic energy to kind of explain what happens in the universe with its expansion. Okay? That's what's going on. She is or he is a plock. What? You're dressed nice. You have a good... Am I dressed nice? Oh, thank you. Oh, yeah. I guess so. I guess this is a nice enough dress. Thank you very much. I did not... Oh, I guess I went out, but that was just for a walk. I went out for a walk. Her membership is called Become a Member. What do you expect, man? My membership is called Become a Member. In fact, I should rename it Become Like Steven. I'll rename it after this. I'll rename the membership Become Just Like Steven. Those pearls look nice. Thank you. They are pearls. One of my best friends gave me these pearls, actually, for my... Well, for my... Actually, these might be from my wedding. Many, many suns and moons ago. See, that is actually good. Good, what is good? Splitting atoms is fission. Fusion is when... Exactly, good! So the atomic bomb, I was going to say atom. Atomic bomb is an example of nuclear fission where a larger nuclei is being split. And then, hello, a kitty cat is over here. And some of the split parts are going in and splitting more atoms. Fusion is when two nuclei come together and make a new element. For example, hydrogen being used to make helium. Become like Steven, he's the GOAT. Thank you, Steven, for becoming a member. Good luck with that, you're already promised. Promised with what? A goat who is an amateur. It's Sachi Mama. Oh, Suji went over there. Wow, Steven, you're my first member. Oh my gosh. Steven, I will make more member-specific content just for you and just for me. And, okay. I think I got everybody for the most part. Thank you so much, everybody, for being here. And please do like the live. Can we get 20 likes? Can we get 30 likes? And Steven, if you could, please repost your book as like posts on Instagram instead of the stories. I don't know if you already talked about this or not in the comments. Then I can actually read your book easier by looking at the posts instead of the stories, okay? What do you mean, Ace Wolf? What do you mean promise to someone? I think it's something like 11 kilometers per second, right? Which in a different unit might be something else. Yeah, that's okay. I think, Steven, it's totally fine. No rush. I just wanted to point out, and I also messaged you on Instagram. I don't know if you saw my messages, but no rush. There's really no rush or urgency. There is really no rush or urgency. I will get to your book in the next couple days as soon as they become posts, and do your thing until then. Raikudo, hello. I know, I am in Steven's DMs. Usually people are in mine, but I am in his. Indeed, I am in his. I'm looking at Steven's like 10,000 freaking stories, and I'm like, Steven, these are stories. Can you put them as posts? But Steven, no worries. Just forget it tonight. Just enjoy the live and then go to bed and don't worry about it tonight, okay? We will read it on Monday. How about that? We will read it on Monday or Tuesday, okay? Steven is a boomer, but we love him. She's in his DMs. I thought marriage was arranged at birth. Hello, looking exquisite. Oh, hello, completely insane. How are you? Hello. Hello, insane. How are you doing tonight? Thank you so much for being here. Can you please like the live? Steven, don't do it now. Oh, you're the only one who listens. Can you do it later? Can you do it in the morning? Don't do it now. Do it in the morning. Can you please like the live? Double tap to like the live, please. Thank you. So the marriage question. My marriage was not my former marriage. I'm currently not married. In the past, my darling. In the past, this marriage was not arranged. Not every Indian has an arranged marriage, if you didn't know. But I end up doing something else. Yes. Can we get 30 likes, please? Now we ask for 30. We're increasing like we increase the weights that we lift. 20 pounds one day, 25 the other, 30 pounds the next day. I'm doing just fine, chilling like a villain. Chilling like a villain. So somebody was asking about marriage. Are you quite done? My marriage is. So, are you done asking about it? So at my former wedding, I received these earrings from a friend. You're not married, wow. Would you ever get married again? Depends who's asking. That was fairly clear to me. A lot of Indian men hit on the streamer I mod for. What? Coco Vita. She ruined greatness. Who? What are you talking about, Dora? Alright, we'll keep going. So, setting aside the technical difficulties that arise when general relativity is involved, we can now discuss the evolution of the universe in broad terms. Okay, we saw this already. In the cosmological setting, the picture is similar, but the critical quantity is not the velocity of the rocket, which is analogous to the Hubble constant. Can we get 20 likes? Aww. Oh, I'm so sorry. I did not know I was your first member. Of course you are, Steven. You're the good boy here. Look at everybody else. Bad boys. Bad. Very bad. You're the good student. Sachi? What's wrong, Sachi? Sachi's feeling extremely ignored. Just like old times. It won't be me, you had to be the first. Dora, stop spreading misinformation. Did you know that my property tax has increased? And that I cannot afford anything anymore? Nothing. I'm drinking Coco Vita. I can't even afford the chickpeas now. Actually, no, I can. Because the chickpeas are cheaper than Coco Vita. Coco Vita, please feel free to send more. And then I will say that this live is sponsored by Coco Vita, which currently is not. I'm not bad. Aww, you're not. Chickpea, you're the best mod. You're doing so good, thank you. Eat meat. Goodness. I should show you this one video I made while eating meat from a Brazilian restaurant the other day. Well, a Brazilian takeout restaurant, because I can't afford to the sit-down ones. So I got Brazilian food, and there was meat in it, and I was chewing and chewing and chewing and chewing and chewing and chewing. Now, why did I do this? Because I am supposed to eat protein, because my friend, who is a man, has been lifting less than me, but his muscles have been growing more than mine, and he's been getting harder and harder. And I was like, wait, what are you doing? And it's because he's eating more protein than me. So I was like, okay, fine, I'll eat meat once in a while. But it's a lot to chew. It takes forever to chew. I so much more appreciate and prefer vegetables. Head on the streets for some fresh coconut water. Exactly. Can we get a super chat? His muscles. Oh gosh. His arms. Can we get a super chat of $500,000, please? Thank you so much. So, we will now talk about if the real density of matter exceeds the critical density, then the universe will eventually recollapse. Its gravitational energy is sufficient to slow down, stop, and then reverse the expansion. If the density is lower than this critical value, the universe will carry on expanding forever. The critical density turns out to be extremely small. It also depends on H0, or the Hubble rate, but is on the order of 1 hydrogen atom per cubic meter. Wow, 1 hydrogen atom per cubic meter. Most modern experimental physicists would consider material with such a low density to be a very good example of a vacuum. So 1 hydrogen atom per cubic meter. So a cubic meter is the volume. So a meter times a meter times a meter is the volume. So a meter length on each side of a cube, that's the volume. And then if you had 1 hydrogen atom in it, that would be the critical density. So this critical density is rather small. So if, depending on who you're asking, well, there's Baji. Depending on who you're asking, they might just call this a vacuum, but of course there's like 1 hydrogen atom, I suppose, So that's the critical density, quite low. Yes, I prefer chickpeas. That's my preferred method of intake of protein. Donate some money. Very true. Okay, so and now at last we can introduce the quantity omega. This is simply the ratio. Wait, I think that's an omega. I'm looking at the symbol and I'm like, wait a minute, what the frick is that? That's big omega. So there is the omega as in the small little omega, which is a W looking thing. Oh my goodness, Fuji. Oh my goodness, you're so cute. Oh my goodness, you're the best. There is the omega symbol, which is the little omega, which looks like a W. Then there's the big omega, which looks like this. Let me write it. Where's my pen? I don't have my pen right now. It looks like this. Whatever, doesn't matter. So, we can introduce this quantity omega. It is simply the ratio of the actual density of matter in the universe to the critical value that marks the dividing line between eternal expansion and ultimate recollapse. Okay? So like eternally expanding would mean that the expansion rate is very high. It is so high that it's just like avoiding recollapse. Like there's not even a question of recollapse. It's just going to keep on expanding and expanding and expanding. We mean the universe. And then recollapse means that the expansion rate is not so high, so it will recollapse. As soon as I post, I'll let you know. Thank you. I needed to get Adam by Dr. Krauss. That's very true. Dr. Krauss, please do send a copy of your book. Will you show your tongue? Don't ban him. Can you guys please behave so that my mods don't ban you and I get my watch hours? Like a horseshoe. Yes! Raikudo, love it. Raikudo is basically saying that the big omega looks like a horseshoe. Acacio! Oh my goodness, let me love that. Super chat. Acacio has done a super chat. Goodness gracious me. Wow. Wow, wow, wow. Acacio 59. Muchas gracias. Wait, did I say that right? Muchas gracias. Thank you so much. Thank you so much, Acacio. Thank you for doing the super chat. Wait, now I can't see. Now I can't do anything. Oh, there we go. There we go. Thank you so much. I was trying to like the chat. Hopefully I did that. Dark Gloom. Hello. So yeah, the omega looks like a horseshoe. So Raikudo is correct. Mr. Benjamin, you're a dashing fellow. How about you stop being that way and listen to her? Hello, Benjamin. That's right. Thank you so much. Dark Gloom says hello, hello. Hello, Dark Gloom. Hello, Chickpea. Just bent outwards at the end. Yes, exactly. Super chat, we're getting an Adam by Dr. Krauss after her property tax. Exactly. The property tax has almost doubled at this place, which makes it very difficult for me indeed. Everybody, if you would like to help pay the property tax, that would be most appreciated, and Acacio already has. Look at that. Look at this property tax help that I'm getting, which thank you so much. Thank you so much. That's correct. Gracias, and I say de nada. Oh, thank you. Gracias. Thank you, thank you, thank you, thank you, thank you. De nada. Welcome. Very nice. So, now that we know what omega is, it looks like that horseshoe thing that Raikudo is talking about. Basically, we got eternal expansion if omega is very high, or the expansion rate. I mean, you can pick a different symbol for expansion rate. This guy is using omega. Some people actually use lambda, I believe. But if this expansion rate is very, very high, then you will just have expansion forever, forever, forever. If the expansion rate is lower, then you would have a recollapse type of energy. Okay. She's a Richie. Not anymore, I used to be. She got a super chat. Thank you. You should donate. Mr. Acacio, thanks so much. Thank you. Hi, Grimmy. Things are so expensive now. I'm not really that rich anymore. Benjamin Robey, do you want to do a $600 super chat, or $600 for you to not get banned, and $4,000 for you to be back tomorrow? Thank you, Acacio. So one of these omega cases, or the expansion rate cases, basically will coincide, will basically apply to the flat case, where the universe is avoiding recollapse, but its expansion is not so um, strong either. It's not so quick either. And the other case is where the expansion rate is a bit lower than the flat case, and we expect there to be a recollapse. And then the third case is where the expansion rate is pretty high, as in it's above the flat case, and we will pretty much eternally expand. Aw, Benjamin. Benjamin is gone. She's a businesswoman. I see. He wasn't gonna pay. Why is he? I know. What was his name again? Benjamin. Benjamin, if you want to come back to the chat, just do a super chat. Do a $50 super chat to be let in again. Chickpea break, you're so cringe. Why? What's Chickpea done? Chickpea is so helpful with the super chats. Grimmy told me you were attacking people for super chat. That's funny. So here's the thing that's inverted again. These are the three cases of these curves. See how the top one if omega is greater than 1, then the expansion will eventually stop and the universe will recollapse. If it is less than 1, the universe will expand forever. Poised between these is the flat universe with omega finely tuned to be exactly unity. We're gonna get more super chats by being extra polite. Yay, thank you. I can't with this guy, no way. Okay, so then the long-term viability of the cosmological expansion is not the only issue whose resolution depends on omega. So the long-term viability of the cosmological expansion What is so funny, Grimmy? Why are you being mean to my friend Chickpea? Thank you for the hearts. Can we get 20 likes? Can we get 30 likes? Can we get 40 likes? Thank you so much. So, as we can see, and to reiterate and kind of summarize, depending on the expansion rate, you will either have a flat universe, you will either have an eternally expanding universe because the expansion rate is too high, or you will have a recollapsing universe because the expansion rate is not high enough. And to explain all of this, he gave the example of the rocket that's launching from the Earth, and depending on the escape velocity, it will either come back down and hit the ground because it could not escape the gravitational potential energy of the Earth, or its kinetic energy is fast enough where it kind of keeps going forever, or it is basically sort of at that critical level. Okay, so what else does this expansion rate mean? So these arguments based on simple ideas of energy resulting from Newtonian physics are not the whole story. In Einstein's general theory of relativity, the total energy density of material determines the global curvature of space. So this energy density stuff that we just talked about has more meaning in general relativity in the sense of a space-time curvature. Because remember that in general relativity, space-time is curved and gravitation is sort of this fabric of the curvature of space-time. And so all of this energy density, matter density stuff that we're talking about has more meaning in terms of what actually it implies in general theory of relativity. Okay, so these arguments based, so once again, even though he used the analogies of the Newtonian physics with potential energy, kinetic energy, the rocket example, to kind of understand, to kind of help you understand what we mean by the expansion rate, actually, what we're kind of talking about here with the energy density of the universe has deeper meaning when it comes to general theory of relativity. So in Einstein's general theory of relativity, the total energy density of material determines the global curvature of space. A space of negative global curvature results in models with omega less than 1. A model with negative curvature is called an open universe model. And open universe model means expansion rate is too high. It's higher than the critical rate. A positively curved or closed model pertains if omega exceeds unity. This is where the universe will recollapse, right? And so remember or note that there are different models in cosmology that allow for different sort of fates of the universe. So depending on if you want the universe to collapse upon itself at some point, or if you want the universe to be open as in expands forever, or if you want the universe to be flat as in the expansion rate is sort of at the critical rate, you can have sort of a different cosmological model that allows for each case. And then what you can do is, yes, Fuji, you can do the math for each of the cases, and then you can see with experiment, you can verify which case is the one that is sort of matching your experimental observations the best. And actually, this is kind of how people do the cosmological stuff, is because in the beginning, they can only have these models. They don't necessarily know all the different parts of their equation and all the numbers that can go into the equation. So they come up with the models and they use these different values of the omega, for example, the expansion rate like we are talking about here. And depending on that expansion rate, you will get a different model of the universe. And then depending on which model, after everything is fitted, actually matches your observation the best, you will know whether the universe is closed, whether it's open, whether it's flat, okay? So hopefully that makes sense. Good night, Grimmy. Hi, Adam. Hello, Adam. Who is purple? So, thank you for being here, Adam. Thank you so much. Welcome to the live. Welcome, welcome. And can we get 20 likes, please? Can you please like the live? Brian? Who is Brian? I called you Brian. What? Called me Brian? I was trying to look for the... Makes sense that it will collapse into a single black hole. So I don't know if it will collapse into a single black hole. It may, like the Big Crunch, if it were to collapse, that could happen. It could collapse back into a singularity. Right now, it's interesting that you mentioned the black hole, because that is the other singularity that we know of. The Big Bang, which is where the universe is thought to come from, was a singularity, as well as a black hole is an example of a singularity. Hi, Fuji. Fuji, Shana, Mama is working, Shona. Fuji, Mama loves you. Fuji's throwing a tantrum. Okay, so I wanted to mention that cosmology oftentimes is done with these models. you don't always know every single part of your equation because you're talking about the entire universe here. So sometimes you plug and chug some of the equations and some of the symbols or variables and you kind of play with it. Basically, you could play with the possibility that the universe is open or closed or flat. And as it turns out, that after doing these models, thank you so much for the hearts. Can we get 20 likes? As it turns out with these models, what is actually seen and matches the observation the best is the flat model. So we didn't just say that the universe is flat like it's our hobby or we wanted to. That is actually the model of the universe after we came up with these cosmological models of the flat, the open, or the closed universe. After we came up with these cosmological models, we actually saw that the flat one matches what we observe the best. And we talked about this in a previous live when we talk about cosmology and cosmological models and dark energy and expansion of the universe. We talked about this. So the universe being flat, meaning the expansion rate is equal to the critical rate, which keeps the universe flat, as in it's not open, it's not closed, it's flat. That is the universe that we observe, okay? So once again, a space of negative global curvature results in models with omega less than 1. A model with negative curvature is called an open universe model. A positively curved closed model pertains if omega exceeds unity. So that same symbol, if it's more than 1, then it would be exceeding unity. In between, there is the classic British compromise universe, poised between eternal expansion and eventual recollapse, which has omega exactly equal to unity. This model also has a flat geometry in which Euclid's theorems all apply. What a relief it would be if the universe chose this simplest of all options. I got my own place and I own everything. Very nice. I don't. I own my land and I built my house. Look at that, Chickpea. Chickpea break. Dang, I wish. I bought mine. I pay a freaking mortgage. Good job, Chickpea break. Which is why I question how much mass would it take where the force of expansion would overtake the gravity the mass generates, like those supply and demand charts. So as far as I know, that's already happening, Raikudo. The expansion is more the expansion is happening in the universe. So it is an anti-gravity term that's winning. I abuse the banking system. What? I only use the bank to save. Thank you for the hearts. MSTR Ronan says hi. Hello, MSTR. Are you in astrophysics, ma'am? Hello, Adam. Yes, I did my what am I even saying? I did my PhD in physics with a subfield of particle astrophysics and a bit of cosmology. So yes, I did physics. My degrees are in physics, and physics, and the focus was in particle astro. Okay. Where is this other comment that I just read? Something about. We will talk. By the way, Raikudo, we will talk more about the comment you made. I'm reading the comments. Chickpea break. With all the money you can give super chats. Go on, best mod. That's true, Chickpea Break. We were not aware that you're so rich. Why don't you give us $500,000 that you're saving from the mortgage? Can you tie ponytail hair, please? Hello, MSTR Ronan. Can you give us $500,000, please? Your face is beautiful. This was more for figuring out how to break a supermassive black hole. Don't walk it back now, Chickpea. Give some money, rich man. Building a house isn't easy. That's true. Hello, Doro. Hi. I'm not rich. Donate some money, rich man. $20 super chat? No! What do you mean? A super chat for ponytail, we asked for $1,000, Chickpea. Are you serious? I don't even have a ponytail hairband right now. I have to make one, and for that I need $1,000. Coco Vita costs $20. Please, 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 please. $100. 100. Cheaping me out. $100. 100. You look like you work at a 7-Eleven, and so what I do? Chickpea Break, give us some super chats. Isn't that how you said it? Donate money to us. $1,000 super chat for a case of Coco Vita and ponytail. Okay. Okay. The quantity omega determines both the geometry of space on cosmological scales and the eventual fate of the universe. So of course it gives us geometry, geometry that we don't always know exactly what it is of the universe, because the universe is very big and we can't see every part of it. So part of this expansion rate geometry, expansion rate thing is about geometry, and partly it's about the fate of the universe, like understanding sort of what will happen to this universe is part of it as well. We did land on the moon. Steven is correct. Gosh. Gosh, oh gosh. Gosh, oh gosh. Gosh, oh gosh. Okay, so it's important to stress that the value of omega is not at all predicted in the standard Big Bang model. It may seem to be a fairly useless kind of theory that is incapable of answering the basic questions that revolve around omega. But in fact, that is an unfair criticism. As I've explained, the Big Bang is a model rather than a theory. As a model, it is self-consistent mathematically and compared to observations, but it is not complete. In this context, this means that omega is a free parameter in much the same way as the Hubble constant h0. To put it another way, the mathematical equations of the Big Bang theory describe the evolution of the universe, but in order to calculate a specific example, we need to supply a set of initial conditions to act as a starting point. Since the mathematics on which the model is based break down at the very beginning, so we have no way of fixing the initial conditions theoretically. So this is because the Big Bang is a singularity. So by definition, mathematics will break at the singularity. The Friedmann equation is well defined, whatever the values of omega and h0, but our universe happens to have been set up with one particular numerical combination of these quantities. All we can do, therefore, is to use observational data to make inferences about the cosmological parameters. Exactly. So we know something about these equations, as in we know what the equation looks like with these variables, but we don't always know the values of everything. We set it up, plug and chug. We set it up with these different assumptions of like what the model is, because we can assume whatever we want. We can play with whatever model, we can assume whatever model we want, and then we infer with observation which one is matching the best, okay? Nathan, hello. Hello. Excuse me. So once again, the Friedmann equation is well defined, whatever the values of omega and h naught, but our universe happens to have been set up with one particular numerical combination of these quantities. All we can do therefore is to use observational data to make inferences about the cosmological parameters. They cannot, at least with the knowledge presently available and within the framework of the standard Big Bang, be deduced by reason alone. Like, you can't just reason everything about this universe and everything about the cosmological parameters. Some of it is you set it up as the equations and then you plug and chug the different models and you see which one kind of matches your observations the best, okay? On the other hand, there is the opportunity to use present day cosmological observations to learn about the very early universe, okay? You're actually crazy. I can see your craziness, says Jay. Do explain, Jay. You can't just call a person crazy. What kind of crazy are we talking? Give us a little bit of a psychological explanation of your commentary here, my darling. Chickpea says, and that doesn't count for sheet. I'll make it happen soon enough. I actually don't have a PayPal or a credit card. I have a private banking card. Oh, that's cool. That's cool that you don't have a card, like a credit card. That's great. Can't even buy stuff online. You don't have a credit card? Dang, man, they're awesome. Thank you, everybody. Thank you, Doro. Thank you, Chickpea. Thank you, Steven. Thank you, Nathan. Nathan, how are you? I told the universe to give lots of money. It became true. Hi, Adam. Something tells me you're fibbing. An attractive crazy. Oh, goodness. Jay, I'm probably your mother's age. Do have some respect. You're probably 16 or 13. Or are you in 7th grade, Jay? Tell us. Isn't it your bedtime? 12:51 in the morning. Watches a tumbleweed roll across the floor. Listens to the crickets sing. I'm 50. It's true. 50. I'm good, got a second job, so working nights at Tractor Supply now. Nathan, what happened to your 9 o'clock bedtime? Maybe 20s by today's standards. What, my age? My age used to start with a 2. I'm 35. Oh gosh. Doro, there is somebody your age here. It's Saturday. Oh, Nathan, are you working on Saturday at the tractor place? And you're gonna be not going to bed at 9 p.m. on Sat and Sun, is that right? I do like this dress. It is blue. I like it. Oh gosh, your gravity is like a blue supergiant. Thank you, my darling. Jay's age. Oh God. I know your age. I'm 29 again this year. Jay isn't lying. Every other weekend. So Nathan, what is your new bedtime, my dear? I wish I looked as nice as... I know the live is free unless you're Jay and about to donate $500,000. All of y'all who are attending the live instead of going outside, you're doing great. You're saving money. You're not paying tips. You're not getting drinks and food and other things outside, which means you're saving money, being home, coming to the live, and donating to the live all your spare change of $500,000 and to a good cause. So thank you so much. And good job, everybody. Support her cosmic research with a small donation. Thank you, Adam. Thank you. I did all that before the live. Doro, excusez-moi, how dare you eat and drink and be merry with your architecture money? Right? Architect? It's 1 in the morning, not much to do outside. Don't say Thank you, everybody. Thank you so much for being in the live, and thank you for doing a super chat. Ocasio, thank you so much. Mike D, thank you. Mike D says hi. I'm in architectural work. Yes, so is Grimme. What's up, little head? Hello, the bears. You think I'm a simp sending money? Oh! Adam! Oh my gosh! Adam sent money. Wow! I can't believe it. Oh my god, it's Canadian! Oh my god, Adam, are you Canadian? Oh my gosh. Oh, I feel so bad. As in, I don't feel bad. I just... Are we harassing a Canadian? Oh, I'm so sorry. Canadians are so nice. Wait, why does it say that I have $26 now? Oh my god, YouTube. YouTube is converting all the Canadian dollars to USD. What the frick? No, Canadians are the best. Adam, thank you so very much. Adam, right? Yes, Adam Dolson. You are a doll. Let me like that super chat. It's orange. How come the colors are all changing? I didn't even know that that was a thing. Thank you so much, and thank you so much for the hearts, everybody. Adam did a 20 Canadian dollars super chat. It even says CA. Wow. Welcome, Canada. Welcome, our friendly neighbor. You look nice tonight, B. Thank you. Adam did it. Adam did it. Adam, you've done it. You're the man, Adam. Wow. Canadian too. Canadian. Learn something. Learn something from this Canadian US. Learn something. Learn something. Look at how nice he is. He has not misbehaved once. Everybody who comes to the class usually misbehaves most of the time, except for some nice people. Adam, the same. Oh, shut up, Jay. Shut up. He put his money where his mouth is. Oh, thank you, Adam. I love Canadian bacon. Canadian bacon, bacon, not bacon. Bacon is kind of like ham, right? It's like I think it's like the bacon that's in an English breakfast, full English breakfast. Is that right? Canadians can get rough ornery. Yes, ma'am. Aww. Thank you, Adam. Thank you so much. I used to work for Walmart and worked. Oh my gosh. Bret Hart, #1 Canadian wrestler. Some are. I know personally not all. What? Not all nice? I think Canadians are generally nice to me. Stop it. Be nice to our Canadian guest. Beckham. Beckham. Bend it like Beckham. Jay, your troll game is weak. They're laughing you off. Best to give up. Russians are nice also. Mike D, are you Russian? Is that what this is? Are you Russian? Is that why you're so direct and rude? Is this what this is? You know, the Russians have an Antarctic base called Vostok. And it's a very dangerous place indeed. Indians are known for being direct and rude. Maybe Indian men. Not me, I'm so sweet. Thank you for liking the live. Can we get 20 likes? Are you from the 11th province? Wow. Adam, Jay, look at you guys. Look at you guys. Thank you so much once again, Adam. Thank you so very much. You're incredibly kind and helpful. Okay, let's keep going for a bit. So the search for two numbers. 30 likes. Well, I wanted to get to 20 likes first before it gets to 30. Can we get 20 likes first, and then can we get 30 likes? I worked for a Canadian company. Those ones did not like Americans, and they were fairly obvious about it. They only treated me slightly better because I was native. Oh. Welcome Native America and Native Canadians as well. Welcome, welcome. Thank you so much for being here. I appreciate the lives about these topics. My pleasure. Good to think about the nature of the cosmos. You are in the right place, my dear. Adam, you're in the right place. I live in the state of insanity. Okay, so the importance of determining the cosmological parameters was recognized early on in the history of cosmology. Okay, so even though getting the cosmological parameters is not necessarily a trivial matter, because it's difficult for us to measure these things or know what they exactly are, and sometimes all you can do is come up with these models and then, as I was saying, kind of plug and chug and see what fits best with observations. Indeed, the distinguished astronomer Alan Sandage, however you said that name, Alan is A-L-L-A-N, Sandage is S-A-N-D-A-G-E, formerly Hubble's research student, okay, that makes sense, once wrote a paper entitled Cosmology, the search for two numbers. Two numbers. Let's see what these numbers are. 2 decades later, we still don't know the two numbers, and to understand why, we have to understand the different kinds of observation that can inform us about omega. So the two numbers, I believe, are omega and the Hubble rate. And let me also real quick check which year this was published in, because some of this might be a little bit old. I think this is, oh, I see. This is from 2001, this book. So actually it's a little old, and some of this might be a little bit outdated, okay? But it's okay, we will still hear from a different perspective than some of the other authors and go from there. Be nice to our Canadian guest. And double tap the screen. Can we get 20 likes? Okay. So 2 decades later, as in 2001, we still don't know the two numbers, and to understand why, we have to understand the different kinds of observation that can inform us about omega, which is the expansion rate, and what kinds of results they have produced. There are many different types of observations, but they can be grouped into 4 main categories, okay? First, there are classical cosmological tests. The idea with these tests is to use observations of very distant objects to measure the curvature of space, or the rate at which the expansion of the universe is decelerating. So the rate at which the expansion of the universe is decelerating or slowing down. So the simplest of these tests involves a comparison of the ages of astronomical objects, particularly stars in globular cluster systems. With the age predicted by cosmological theory. I discussed this in chapter 4, so we haven't seen him discuss it yet, but because if the expansion of the universe were not decelerating, the predicted age depends much more sensitively on the Hubble constant than it does on omega. So certain different interesting implications come from the different sort of what something means. So basically, if the expansion of the universe were not decelerating, that has certain implications, such as the predicted age will depend more sensitively on the Hubble constant, or h naught, than it does on the expansion rate. That's just a detail or some fun fact about all this. And in any case, the ages of old stars are not known with any great confidence. So this test is not a powerful diagnostic of omega at the moment. So sometimes, they use certain observations that are itself a little bit questionable, such as the ages of these very old stars, like what this author is talking about. Like sometimes, like understanding those ages itself is a challenge, and maybe they can be sort of a reference, but how accurately they tell us anything is also sort of questionable, okay? So let's see, other classical tests involve using the properties of very distant sources to probe directly the rate of deceleration or the spatial geometry of the universe. Some of these techniques were pioneered by Hubble and developed into an art form by Sandage. They fell into some disrepute in the 1960s and 1970s because it was then realized that not only was the universe at large expanding, but objects within it were evolving rapidly. Steven, you can do it next week. No rush. Do it like Monday or Tuesday and we will read it then, okay? There is no rush, Steven. Because I think tomorrow we'll talk about more cosmology, and then Monday or Tuesday we can read your book. What? I'm encouraging him to rest. And sometimes that encourages people to do more work. He's an American. If I tell him to rest, he'll probably work more. He's not French. This book is called Cosmology, A Very Short Introduction. See how this is a very tiny little book from the library. I got it from the Malden Public Library, actually. Or actually, this is part of Boston Public Library system.